Hello everyone, I welcome you all for the lecture series on food technology. Today we are discussing the topic on spectroscopy. This topic is divided into these modules: introduction, importance of spectroscopy, elements of empirical spectroscopy, electromagnetic spectrum, and absorption of radiations and applications of UV absorption spectroscopy and their advantages, and we will conclude this in the end. Coming to introduction to spectroscopy. The spectroscopic techniques from the wide range and most important techniques used in chemistry and physics. These techniques provide a large range of qualitative and quantitative data. Most of the spectroscopic techniques are more or less depending on the emission or absorption of electromagnetic radiation of certain energy changes within an atomic or molecular system. The changes in energy are associated with a complex series of discrete or quantized energy levels in which atoms or molecules are assumed to exist. The use of spectroscopic techniques in analytical chemistry is in the determination atomic and molecular structure, including functional groups, photochemical process and stereochemical arrangements. Various spectroscopic techniques are used currently because they require a very small amount of material and short interval of time for analysis. Modern spectroscopy and its advantages form a significant part of modern chemistry, physics and technology. The word spectroscopy means the watching of images, but the modern subject covers the interaction of electromagnetic radiations with matter. The very important effect of such interaction is that energy is absorbed or emitted by the matter in discrete value called quanta. The absorption or emission process of the electromagnetic spectrum range from the gamma region, that is nuclear resonance absorption or the Mass-Beer effect, to the radio region, that is nuclear magnetic resonance. When the measurement radiation frequency is done experimentally, it gives a value for the changes of energy involved, and one can draw the conclusion of studied about the set of possible discrete energy levels of the matter. The experimental measurements of radiation frequency emitted or absorbed and the energy levels derived from these comprise the practice of spectroscopic techniques. In many spectroscopy branches, the system interacts with the electric field, but in case of magnetic resonance spectroscopy, it interacts with the magnetic field. Spectroscopy is powerful technique available for the study of atomic and molecular structure and is used in the study of a wide range of sample to get the data. The study of spectroscopy techniques can be carried out as follows. Atomic spectroscopy: the interaction of electromagnetic radiation with atoms which are most commonly in their lowest energy state called the ground state. Monoatomic substance normally exists in the gaseous state and is able to absorb electromagnetic radiation, leads to transition of electrons from one electron energy level to another. The electronic absorption of electromagnetic energy can occur only if the photon has an energy which is equal to the energy difference between two quantized energy levels, that is delta E is equal to h mu, where delta E is the energy difference between two levels and nu is the frequency of photon which can result in the electronic excitation. Application of atomic spectroscopy in the field of physics and chemistry are few. However, its demand has increased by the development of lasers. Coming to molecular spectroscopy, the interaction of electromagnetic radiation with molecules, these results in transition between rotational and vibrational energy levels in addition to electronic transitions, which gives the spectra of molecules are much more completed than those of atoms. Molecular information may be obtained about molecular vibrations and rotations that reveal a great deal about molecular structure. The detailed information regarding molecular structure, molecular symmetry, bond distances and bond angles and physico-chemical properties like electronic distributions, bond strength and intra and intermolecular processes are obtained from the atomic and molecular spectroscopy. The spectroscopic investigation find were first carried out by Sir Isaac Newton in the 17th century. The quantitative analysis was possible only after the introduction of quantum mechanics. Initially, it was atomic spectra that provided the empirical evidence for the various quantum mechanical ideas. Coming to near infrared spectra, in the absence of any of the electronic transition, no change in electronic state, vibrational transition can occur, that is, there is a possibility of a transition from one vibrational energy level to another with the same electronic state of the molecules involving in energy changes of about 0.1 eV, that is 1.6 into 10 to the power of minus 20 ERG per mole. Frequency of radiation will be calculated by using this following formula. This observation shows these radiations accompanying vibrational changes within the electronic ground state should appear in near infrared portion of the spectrum. The vibrational transition within a particular electronic state would be associated with a different possible rotational changes, which results to the presence of a number of closely spaced spectral lines. These are observed in absorption in the wavelength region of about 1 to 20 micron. For a diatomic molecule, the mode of vibration is only one, hence only one vibration rotation band for each vibrational transition. Coming to far infrared spectra, in the far infrared region, transition occur that are purely rotational in character, unaccompanied by changes in electronic and vibrational energies. Such a transition involves an energy change of 0.005 lambda, and thus frequency of radiation is calculated by using following formula. It is observed that these radiation will lie in far infrared region. The bands in the far infrared region are therefore called rotational spectra. Coming to importance of spectroscopy, the electromagnetic spectrum is one of the most widely used techniques of analysis. It is used in all branches of chemistry and environmental laboratories because many substances can be selectively converted to a colored derivative. The technique is readily available and generally fairly easy to study. It will explain the absorption of radiation by molecules and its relation to molecular structure. Make accurate calculation relating the amount of energy absorbed to the concentration of an absorbing analyze and explain the instrumentation required for making data. Data can be made in the infrared, visible and ultraviolet regions of the spectrum. The radiation energy region of choice will depend upon the availability of instruments, whether the analyte is colored or can be converted to a colored derivative, whether it contains a functional group that absorbs the ultraviolet or infrared region, and whether other absorbing species are present in the solution. IR technique is generally less suited for quantitative measurements, but better suited for qualitative or fingerprinting information than our ultraviolet and visible technique. Visible optical technique is generally less expensive and more available than UV spectroscopy. Coming to elements of empirical spectroscopy. The spectroscopic methods used in various regions of the spectrum naturally differ widely from each other in construction. These experimentally observed differences will be discussed, but here it will probably be helpful to indicate the basic ideas which are common to all the types of spectroscopic techniques separately. Coming to absorption techniques, the block diagram shows the components of an absorption spectrometer which might be used in the higher, visible and ultraviolet regions. The radiation energy from a white source is incident on the sample and then it is connected to analyzer. This leads to the required frequency reaching the detector at the time interval. The signal later passed to a recorder which is connected to an analyzer so as to get a trace of the absorbance as the frequency varies. This electronic device interrupts the radiation beam a certain number of times per second, usually fixed somewhere between 10 and 1000 times, and this detector sends an alternating current to signal to the recorder with a fixed frequency of 10 to 1000 Hz. The two main advantages of these techniques are the amplifier in the recorder can be of AC type, that is simpler to construct and more reliable in operation than ADC amplifier, and the amplifier can be tuned to select only that frequency which the modulator imposes on the signal, neglecting all other signals. By this method, other extraneous signals are removed from the spectral trace and a better accurate spectrum results. In the microwave and radio frequency ranges, the monochromatic sources whose emission frequency can be varied over a range are to be selected. Figure shows no analyzer is necessary, the source being in a sense its own analyzer. Now, it is necessary for the recorder to be synchronized with the source scanning device in order that a spectral trace be obtained. This is the typical diagram of scanning absorption spectrophotometer. Coming to emission instruments, schematically a typical spectrometer, the excitation can be thermal or electrical, but usually takes from electromagnetic radiation. In the later stage, it is essential that the detector does not collect the radiation directly from the exciting beam and the two are placed at a right angles as shown in figure. A modulator fixed between the source and the sample together with a tuned detector amplifier ensures that the only emission recorded from the sample arises directly from excitation by neglecting other emission. Coming to electromagnetic spectrum and absorptions of radiation. The type of electromagnetic radiation in order of their increasing wavelength or decreasing frequencies are known as complete electromagnetic spectrum. The visible spectrum represents only a small part of the electromagnetic spectrum. If all the types of electromagnetic radiations in order to their increasing wavelengths, then the portion above the visible region is called infrared white, the lower it is the ultraviolet region. Infrared have higher wavelength, that is less energetic. Cosmic rays carry high energy while radio waves it is the least energetic one. Microwaves have larger wavelengths and are used in telephone transmission. All types of radiation travel as waves with the some velocity, but differ in their properties. For example, X-rays can pass through glass and muscle tissues. Radio waves can pass through air. Visible ultraviolet and infrared radiation can be bent by reflection or diffraction in a prism. When light radiation is penetrated through an organic sample, some of the wavelengths are absorbed while others belonging to that radiation remain unaffected. A molecule can absorb radiation of certain frequencies if there exists within a molecule an energy transition of magnitude, that is delta E is equal to h nu. It is observed that when light radiations are passed through an organic sample, then electrons of the sample's atoms are excited to higher level. Also, the vibrational and the rotational energies of the molecules are completely quantized. Therefore, the wavelength of the light absorbed by molecule will be due to the changes in the electronic, vibrational or rotational energy levels allowed for the atoms. The wavelength absorption can be measured by using spectrophotometer. If we plot the changes in absorption versus wavelength, then we get some absorption band which is highly characteristic of a sample, and the experiment provides a tool to measure the molecular structure of an unknown compound. The electromagnetic spectrum can explain the followings. The visible and ultraviolet region radiation wavelength, that is between 200 to 800 millimicron, the absorption of radiation in this region results the excitation of pi electron in a conjugated or an unconjugated system. In the conjugated system, the separation between the ground state and the excited energy level will be less, and hence absorptions occurs at a longer wavelength. In the case of carbonyl group, an aldehyde or a ketone absorbs some characteristic wavelength. Hence, an UV or visible spectrum is useful for the determination of conjugation carbonyl group and will not give any other information about the remaining part of the molecule. Infrared radiations covers the wavelength from 0.8 to 2.5 micron is called near IR region, 1.5 to 25 micron is called far IR region, and 2.5 to 15 micron is useful region for IR spectroscopy. Hence, these radiations are of higher wavelengths and less energetic. The absorption of radiation by an organic sample in 2.5 to 15 micron range causes the changes in the vibrational levels or results by the changes in rotational levels. Thus, certain bands appear which characteristically absorb for the stretching vibrations and are very useful in structure determination. The absorption at higher wavelength in the IR region are the characteristic of a compound and also help in distinguishing one compound from the other. Although more helpful than ultraviolet method, it does not give complete information about the environmental effects in a molecule. NMR spectroscopy gives a complete insight into the environment and the arrangement of atoms within a molecule. For this method, radiations of longest wavelength range radio waves are useful. A simple underfunding is placed in a strong magnetic field and irradiated with radio waves. By using the strength of the magnetic field applied, radiations of the definite wavelength will be absorbed, which gives the nuclear magnet's specific orientation with respect to the applied magnetic field. Application of UV absorption spectroscopy to organic compounds. Coming to detection of conjugation, it gives the relationship between the different groups, particularly with respect to conjugation. The conjugation may be a relation between two or more carbon-carbon double bonds or relation between carbon-carbon and carbon-oxygen double bonds or relation between double bonds and an aromatic ring. It can observe the presence of an aromatic ring itself and the number and locations of substitutes attached to the carbons of the conjugated system. Coming to detection of geometrical isomers. In the geometrically isomeric compounds, trans isomeric exhibit lambda max at slightly longer wavelength and have a larger extinction coefficient than cis isomers. Detection of functional groups. It is possible to determine the presence of some functional groups using UV spectrum. Even the absence of any absorption above 200 nanometer is of some utility, since it shows the absence of conjugation, carbonyl group and benzene rings in the compound. Coming to qualitative analysis, UV absorption spectroscopy can give the information about those types of compound which absorbs UV radiation. These compounds are with unbonded electrons or those with the conjugated double beam system and aromatic compounds. Determination is done by using the absorption spectrum with the spectra of known compounds. Coming to determination of impurities. UV absorption spectroscopy method is used for detecting impurities in organic compounds. The main aim of the superiority of this method are the bands due to impurities are very intense, that is, an impurity having an around of 0.05% has a sigma value of 2000. Therefore, such an impurity can be observed in a transparent major component. The organic compounds can be classified into saturated compounds having the little absorption and unsaturated compounds having strong absorption bands. The common impurity in cyclohexane is benzene. Its presence can be easily detected by its absorption at 255 nanometer. Coming to quantitative analysis, quantitative determination of compound that absorb UV. This determination is based on calculated by Beer's law. Coming to molecular weight determination. Molecular weights of compound can be measured using UV visible spectrometer provided suitable derivative of these compound could be prepared. This technique is based upon the formation of a derivative such as picrate, and this is determining from the molecular weight of any amine. First, it is converted into amines picrate. Then, a known concentration of the amine picrate is dissolved in a liter of solution and its optical density is measured at lambda max equal to 380 nanometer. The main advantages are the spectrophotometer technique is sensitive about 1 part in 10 to the power of 8 or 1 microgram per ml in many determinations. Fluorimetric techniques possess greater specificity than spectrophotometric technique because there is selection wavelength not only for the radiation emitted, but also for the light which excites the sample. The fluorometer results affected not only sensitivity, but also the precision. The general application of spectrophotometers are finding the chemical structures and processes, analysis, that is determining of impurity, estimation of single component vitamin, investigation of fluorescent intensity of the sample compound, finding of 3,4 benzpyrene, finding of rare earth terbium, investigation of bismuth. Coming to conclusion, the important technique of spectroscopy unit explains the techniques of spectroscopy with modern spectrometer. The study of these instruments used in spectroscopy to explain in detail for various uses of UV and fluorescence spectrometers presented properly for studying detailed usage of UV and fluorescence with examples explained, which can be important role for many applications. Detailed advantage of UV and fluorescence with examples are given this unit. Thank you.